Data ingestion pipelines frequently bottleneck at the very first step, taking chaotic, unstructured data and forcing it into a highly structured, rigid database. Flat file formats like CSV and JSON are incredibly flexible, which is exactly why they resist direct insertion into relational databases. They do not carry strict data type definitions within their structure. Engineers perform tedious manual labor. They inspect sample rows, guess the data limits, and manually write DDL code. Engineers can use statistical algorithms to guess these data types automatically, but those basic scripts fail to understand domain-specific constraints. They see text, but they lack the ability to comprehend what that text actually represents. Because they only guess the physical shape of the data, traditional ingestion pipelines remain incredibly brittle. They parse the characters while completely ignoring the actual business meaning hidden inside those rows. SchemaInfer AI is an open-source tool designed to entirely eliminate the need for manual database schema authoring. It achieves this through a specific architectural thesis, bridging deterministic statistical analysis with large language model-powered semantic recognition. When a raw CSV or JSON file enters the system, it splits into two parallel processing tracks, a statistical layer and a semantic LLM layer. They operate independently, then synthesize their findings to automatically output production-ready SQL tables with strict constraints. This architecture turns database schema definition from a slow, manual engineering chore into an automated programmatic pipeline. To break down this pipeline, we start with the initial ingestion of an ambiguous raw JSON dataset. The statistical layer maps basic parameters, sorting raw input into blocks of integers, floats, booleans, and dates. Instead of a small sample, the profiler scans entire columns to calculate exact null-value ratios. Simultaneously, it tracks repetition to automatically identify enums. This mathematical sorting is incredibly fast. However, it falters when evaluating generic string formatting. A deterministic profiler looks at an email address and a randomized alphanumeric user ID, and it sees the exact same thing, an ambiguous string of text characters. Because this layer operates purely mathematically, it requires zero external dependencies, making it secure to run locally. Statistical profiling is mandatory for determining how much memory a database needs to allocate, but it is entirely insufficient for enforcing actual data integrity rules. To solve the string problem, the pipeline activates the semantic layer. This track triggers specifically when the deterministic profiler encounters those ambiguous string arrays. The data flow routes an ambiguous string profile through OpenRouter. This gateway sends the profile to an external LLM, GPT-4o Mini, which identifies formats like URLs, emails, or phone numbers. The LLM then processes this context to generate descriptive summaries and suggest SQL constraints. Layering a semantic API over deterministic data allows the system to accurately translate raw text into enforced business logic. Before the pipeline generates any executable code, it must mathematically verify the reliability of the ingested dataset. Running parallel with semantic parsing, the Data Quality Report module continuously calculates column-level health metrics. This dashboard displays column health charts. The first calculates completeness, comparing valid entries to missing values. Next, the uniqueness metric evaluates value repetition to isolate the primary key. Finally, an outlier detection mechanism isolates statistical anomalies so they don't skew the schema. Once calculated, these data quality metrics are appended to the main metadata payload alongside the LLM's constraints. This reporting mechanism prevents garbage data from defining your long-term storage architecture. By embedding these quality metrics directly into the pipeline, the generated schema is based on the statistical reality of the entire dataset, not just the first 10 rows. With the statistical profiling and semantic analysis complete, the pipeline enters its final phase, compiling the gathered metadata into executable database instructions. This requires navigating the fragmentation of SQL dialects, as different database engines utilize varied syntax. A compiler node routes metadata into PostgreSQL, MySQL, SQLite, and BigQuery syntax blocks. It generates specific differences for each engine. For PostgreSQL, it applies native UUID types. For SQLite, it adjusts for a weaker typing model, converting those same UUIDs into basic text. Autonomous dialect compilation allows back-end teams to pivot their underlying storage infrastructure without ever needing to rewrite their ingestion scripts. SchemaInfer AI provides a few different deployment interfaces to integrate into existing developer environments. For seamless headless automation, engineers can execute the entire pipeline using the command line interface. For visual schema exploration, it includes a browser-based Streamlit UI, allowing developers to manually review the tables before deployment. However, routing data to an external API introduces a critical enterprise security concern. Highly regulated environments cannot send proprietary data profiles to external LLM endpoints. This diagram shows how the system addresses that risk through mock mode. When activated, the system bypasses the Open Router API entirely, severing the external connection while the rest of the ingestion pipeline functions normally. Mock mode allows secure environments to leverage the deterministic capabilities fully offline, sacrificing only the AI semantic descriptions. There is one final detail regarding the operational architecture of SchemaInfer AI, found in the origin story of the repository itself. This system was not authored by a human engineer. The initial commit logs reveal that the core logic, tests, and interfaces were built autonomously by an AI agent named Neo. This illustrates the concept of recursive AI generation. Systems are learning to design and deploy the highly specific tools they need to operate. AI models are autonomously building the complex infrastructure pipelines required to feed structured data to other AI systems.